Thank you very much. Thank you for the organizers for this unusual event. I've never been speaking to so many high school students in my life. And I've spoken at Rotary clubs many times, but not for students. And unlike you, I want to start by saying that when I was a student, I wouldn't have understood anything of everything. When I was a high school student, anything that you've heard so far. Okay? I'm impressed with your questions, really. And I was a mediocre student, as you can imagine. So I'm going to talk about something that you probably have never heard about, and including the scientists in the room, except for those who work in this subject, and who are more physics-oriented. This is about light-matter interactions as seen in quantum electrodynamics, another version of quantum physics. I'll come into that in a second. And the reason for my title is because there was so much skepticism about when we published the first paper about 7 or 8 years ago. We demonstrated some changes I'll talk about in a second. That I essentially, a colleague of mine just said, "Why don't you just call it alchemy, since nobody believes it?" So this is what it's about. So I'm going to take a little journey, and to explain what I'm doing, I have to go through a path. And I'm not going to come to what I want to say until quite far into my talk. So light-matter interactions are ubiquitous around us. We are talking to each other, we can see each other, the light, the projector, everywhere in our life, telecom, everything you're using, your smartphone, everything that the internet uses light-matter interactions. They're so much around us that we don't even think about it. The light comes through your lens, switches a molecule, like in this photoisomerization. It happens in about 200 femtosecond or something like that, and it switches, and you get this mechanical, physical change, essentially an optomechanical event, which triggers a change in your membrane, and this gives you an image eventually further up. Light-matter interactions, of course, essentially in the biosphere. We wouldn't be here, especially in this part of the world. And I come from this part of the world too. I spent my youth playing in the granite north on the coast here when I was very young. So these are in here. There are lots of interesting events going, physical chemistry phenomena that go on, and I'll come back to that later on. But they are absolutely essential for us, for existence. But what is more, and everybody knows this, but most people don't. Oh yeah, so here, sorry, I forgot about this. I wanted to introduce states, but Päivi before introduced molecular states. It's very important. Everything I'm going to talk about is that molecules have different energy levels. You know that, and probably you all know that. I didn't know that when I was in high school, so I put this up. And these are electronic states, and then there are sub-level vibrational states that superimpose and gives rise to these broad peaks for chlorophyll, which gives rise to the green absorption. So light is absorbed by a molecule like in your eye or in a plant. At the level of the molecule, one photon is a huge amount of energy. Okay, huge. You can make a little calculation to estimate what that is, and so it gives rise to new chemistry and all kinds of other interesting events, which is then stored by the plant. What is much more or much less obvious is the fact that even in a droplet like this, there's light-matter interaction. And I, as a physical chemist, as pointed out, somewhere between physics and chemistry, you never learned this. Actually, no chemists learn this. Physicists learn this, but chemists don't. And even in the dark, there are light-matter interactions. So how can there be light-matter interactions in the dark? And that's where most people start getting a bit lost. And so then I have to bring you back to some history. To understand that, you have to look into the history of our understanding of vacuum. So vacuum, the discussion about vacuum has been going on for thousands of years. In the Western world, it's Aristotle and Democritus Democritus is one who gave us atoms, notions of atoms. They didn't disagree on this. Aristotle thought there was no such thing as vacuum. Democritus thought there had to be some, because otherwise there had to be space between the molecules, for example, for things to mix, like sugar in water or a dye dissolving again in water. And in this debate, however, Aristotle's views was the view that was held in the Middle Ages in Europe until the beginning in the sort of 17th century. And then people started doing modern science, and they had vacuum pumps. This is kind of surprising. Actually, vacuum pumps had existed for far longer than that, but they started doing modern experiments. And there were three people, Italian, German, von Guericke, and Blaise Pascal in France, who actually made vacuum in different ways, and in different systems. The most famous one is the von Guericke one, done in Germany, where he took two half spheres of metal with a liner, pumped it, probably with a hand pump, and he went in a village, and he couldn't, nobody could separate the two half spheres, and then he let air in, and he could separate them. And this looked like magic. So he had to then repeat it in front of the king or the local prince, and this is sort of the Instagram from 1654 of this event. Here you have the two half spheres, 8 horses on both sides trying to pull this sphere apart. They can't do it, and then he opens the thing, he lets air in, and it works. He can separate them. But that was a big public type of thing, but Torricelli and Blaise Pascal their experiments perturbed the scientists. Why? Because they did vacuum in glassware. And one of the things that perturbed them was the fact that light went through what they thought was empty. Of course, it wasn't totally empty. They weren't very good vacuum pumps, but they thought they were empty. And so there was no matter inside or nothing inside, and light still traveled through this glassware. And this was perturbing because they thought there was a medium, that light had to travel in a medium. And so people like Huygens, Newton, they sort of had to grudgingly accept that there were something called ether, something that remained, an unknown substance that remained after the vacuum was pulled on these systems. And that actually survived through Maxwell's equations, which is kind of amazing to me. And until Einstein came around and came with relativity, general relativity, and then suddenly vacuum was just, now we are changing the meaning of vacuum here. Here I'm switching over. Vacuum is now just space, three-dimensional space, and that three-dimensional space had nothing in it, and light traveled in that three-dimensional space, and light followed the curvature of the gravitational, how space was curved by gravity and so forth, but there was nothing else in there. And this new version of space, which lasted only about 20 years, because then people tried to quantify fields. Okay, and this with Dirac tried to quantify things, how things interacted at the distance. So for example, ask yourself, how does a positive charge know the existence of a positive charge a nanometer away, 10 nanometers away, or it's a negative charge? How do they? Okay, that you can ask me afterwards. I won't answer the question now. Okay, but these are the kind of questions that they were asking themselves, and out of this came quantum electrodynamics. It's much more complicated than what I'm showing you, explaining you now. And in this notion of quantum electrodynamics, vacuum, meaning space, is full of activity. Particles are being formed, disappearing moment in a sort of temporary way. And that's how, and this fills space everywhere in the universe, including here. In your head, in your brain, in my hand, everywhere. So there are many types of fluctuations. There are things related to particles, and I'm more interested in the electromagnetic part. So, but just to show you how much is going on in between in the space, if you empty even out in the universe, if you look at the speed of light, just look at the speed of light. This comes from Maxwell. It's inversely proportional to the dielectric constant of vacuum. It's called permittivity, but you might as well call it dielectric constant, and permeability, the magnetic response. You can see the speed of light that vacuum, meaning space, has a dielectric constant. How can nothingness have a dielectric constant? You already see a problem right away. Okay? It has a magnetic response too. These actually is the drag on how when light travels through space, it gets slowed down. It's like walking in water or something on a beach. And the interesting thing is that it's very close to that of glass. So if you read books on this, which I have done to try to understand all this, you realize that actually contemporary quantum field theoreticians think, or at least some of them think of vacuum as a dielectric, meaning a non-metal. Okay? Like that you can manipulate. So, now I'm going to just talk about the vacuum electromagnetic fields. I learned a few years ago that there were various kinds of vacuum fields, and I'm just going to talk about the vacuum one. So what in QED, light is treated the same way as matter. So light doesn't just come out of a lamp, out of these lamps up here on the projector. It actually goes from a state in matter to a state in vacuum, in space, essentially. I mean, I'm not meaning material vacuum anymore. There's no more material vacuum in any of what I'm going to talk about. Now I'm sort of a physics meaning of vacuum. And so it turns out that space has because it's infinitely big, has an infinite number of such states, and that's where the bosons go. Like there can be many in one state, as you know. We heard this from Päivi Törmä. And all these states have Heisenberg's uncertainty principle attached to them, so they fluctuate. And this gives rise to background fluctuations everywhere. Okay, absolutely everywhere. And they impact chemistry in a big time, and this has not been understood, and that's where we come into the picture. So here's some representation of such fluctuations from an Australian website that I found. These fluctuations are now detected because sometimes I have physicists come to me and say, no, there's no such thing as vacuum fluctuations. Well, they are now observed experimentally. There are 2 papers, one from Constance and from ETH, which shows that indeed you can catch them. You can see them. They play a role in chemistry. I learned all this about van der Waals forces. When you're a physical chemist, that's one of the things you learn. And you learn that there are fluctuating dipoles that gives rise to London dispersion forces. But as you can, the question is, where does the fluctuating dipole come from? Well, it comes from the fluctuating electromagnetic fields that are everywhere. And these are not negligible forces. So the forces are so strong that if our hands were it holds my skin together or your skin together. So if our hands were totally flat and I shook Stefan Hell's hand or somebody like that, we have very smooth hands, we shook our hand, we need surgery to separate us. So you're glad your hands are not so smooth. And you don't shake hands like in France, well, like we do in France. Anyway, so that's where light-matter interaction plays a role, even in such a thing inside a droplet. And so you can imagine that you could put a droplet inside a cavity and isolate it from the universe. You can do that already. You can stop molecules from fluorescing, for example. Things like quantum yield of fluorescence, which I was told is something inherent quantum yield, inherent lifetime, those are not inherent. It depends on the availability of these states around us and everything, availability of the states for the light to go into. So I'm not going to talk about the weak coupling, but that plays a big role. I'm going to go switch to strong coupling, because in half an hour I don't have time to do that. So physicists look at light-matter strong coupling in 2 regimes, weak and strong. Weak, you modify radiative properties of light coming out of an emitter, for example. And in the strong coupling, the interaction is so strong that you have new energy levels in the material. And the way to understand this is to look at coupled oscillators. So coupled oscillators was understood by Huygens. We heard about Huygens already today, the pendula clocks. He invented that. And in his time, in 1650, this was a revolution. This was serious. This was like the GPS of today, okay? The atomic clock today. It was the first time that you got fairly precise time, which saved considerable amount of lives and ships and so forth, because you could determine your position more precisely. And he, when he was making this, he must have had more than one, because he noticed that the clocks got synchronized, and he wondered why. And he solved the coupled oscillator model shown here. And here's a modern YouTube version. I'm going to show you with 5 metronomes. Everybody knows here what a metronome is for music, to set a beat, regular beat. And so here's 5 metronomes out of sync. And this should have sound, I hope. Oops. It's always like, what? Don't tell me today. Sorry. You can hear and see everything at the same time.
No, I'll move it back.
okay? I did this in a music store. The guy thought I was doing magic, okay? This is the magic of science. So, you see, they're all synchronized. They're all moving together. How they do that? So they are actually exchanging energy. And that's why they need to be on those empty beer cans, because they have to, they give each other a kick, and they go into a new ground state. They synchronize and go into a new ground state, just like here. This is very similar to H plus H forms H2, and you have to get two orbitals. I mean, if you're a chemist, that's a very, very similar analogy. So here, when they want these new states, you can do it turns out you can do absolutely the same thing with light and matter. So you can couple an optical resonance of anything. It can be a surface plasma, as we heard about, a cavity resonance, with a material resonance. As long as they're at the same frequency or same wavelength, on the right conditions, they will start talking with each other. Instead of exchanging mechanical energy, here they will exchange virtual photons. So a molecule, even the transition dipole moment of a molecule that gives rise to the color, that gives rise to the transition from one state to another, fluctuates. They all fluctuate. A cavity also fluctuates, even in the dark. And so they can interact here. These are virtual photons. Don't ask me what that is. Maybe you can ask some of the quantum physicists in the room what they are. Anyway, they exchange photons, and they give rise to new states. These are exactly the same principle as making J aggregates. We talked about J aggregates before. That's how J aggregates are used. I have a slide with J aggregates. I took it out because I don't have time to go through that. But J aggregates talk to each other. The transition dipole moments are aligned and talk to each other and give new hybrid states. The crazy thing here, and that's where most, at least chemists and even physicists, sort of blank out, they're hybrid light matter states. So now you have a wave function that has a photon content, electronic content, and it's hybridized, and you can give rise to hybrid light matter states and hybrid light matter particles, sort of quasi-bosons, quasi-fermions, whatever you want to call it. And how do you do this experiment? So I skip all the theory. So how do you do the experiment? So it's very simple. Conceptually it's hard, but experiment is very simple. You take a glass slide, evaporate 20 nanometers of silver or gold, spin coat molecules on top, come with a second mirror, and make sure that layer of molecules is just thick enough that the cavity resonates, has an optical resonance, same frequency as the molecules. And then, like here, and then this cavity here is tuned to this molecule here, and then you get two new absorption peaks. And if you're a chemist, this means a new molecule. Okay? The thing is that most of the physicists who worked on light matter strong coupling worried about the optics. For me, I was stimulated in doing this because I read an article on cavity quantum electrodynamics 30 years ago, and I wondered what it did to matter. And what essentially you have is you have to go from here to here by synthesis would take 6 months of research. Here you just close the cavity, and you get this. You can remove it, and it goes back to the original state. And if you have a system like that, it has to be different. It has to have different properties. This is obvious to any chemist, but the problem is that chemists don't know QED, and I'm just at the interface, and that's where I come in. So the other thing that is important to understand in what I'm going to say is just like there are 5 metronomes in the other thing coupling, all moving together. In our cavity system, the optical modes are roughly in the visible are roughly micrometer cubed. Molecules is a nanometer cubed. So you can pack a lot of molecules into the cavity. And from a quantum mechanical point of view, you have to sum over all the possibilities. One cavity mode can interact with 100,000 different molecules. Then you normalize and do all kinds of little tricks, and you end up with a very large collective splitting. You get instead of 5 metronomes, you have 100,000 metronomes, all doing this. So all the molecules, electron clouds, all the molecules are oscillating. And we know this because there have been experiments done, including in Pavy's lab, where you see coherent emission from molecules far apart, micrometers apart. And the crazy thing about this is that when you keep on adding molecules to the cavity, the electronic structure of each molecule changes. First, you get these collective states, which are interesting from transport, conductivity, and so forth, but you also get that all the gaps are changing. That's as if people came into this room, people started leaving, we got smaller and smaller and smaller. The ones who remain, people came into the room, we started getting bigger and bigger and bigger again. It's kind of weird. And this is, real. This is not just, we see this in experiments. So you start off with a molecule like this. You end up, I've just shown 3 states, the ground state and two excited states. Here, if you switch from that to that, as I said before, you don't have to excite the material. Just the fact that you change the eigenstates of the material changes the properties. That's exactly what Pavey was saying before. It's the electronic structure which determines all properties, whether you occupy them or not. And so it's pretty obvious that they should change. So we have looked at a number of things, and I'm just going to talk about material properties and molecular and chemistry. And I've chosen to talk about chemistry. So chemical landscapes are not these simple bars that I showed you before. Those are representation of actually landscapes of potential energy surface that are very complex. And here's an example for this isomerization reaction. There's a ground state barrier here. Generally, when you learn this in school, you just see a little barrier between reactants and products. But an excited state could be reverse. You spontaneously isomerize. That's what happens in your eye. And so another thing that's very important in molecules is that you have all these vibrational modes. And they play a huge role. So in a typical molecule, like the ones I'm showing here, there are probably 100 vibrational normal modes. So they play a role also, of course, in chemical reactivity. So when we first did the experiment, the first proof that you could modify properties on the light-matter strong coupling, non-optical properties, just a property, a basic property of the material, was an experiment we did in 2010. It took a couple of years to publish it. And we showed that the photochemistry of the excited state was modified. This was the paper that gave the word alchemy, because the first time in my life I got a referee report that said, this is not science, this is science fiction, reject. It's the shortest also referee report I've ever gotten. And this the editor, of course, believed. Luckily, eventually Angewandte Chemie published this paper, and since that we moved on. In this paper, we speculated that while the excited state is interesting, it would be much more interesting to look at ground state chemistry and just couple a vibration. But the vibration is tiny in energy. The energy of vibration most is tiny, 1/10 or at least of an electronic transition. So would that really perturb anything? We had no idea. It turns out it has a huge effect, way beyond what we imagine and way beyond our understanding. So to do this, we had to switch now to cavities in micro. The advantage of working in the IR, the vibrational bands of a molecule are at typically 10 microns. And so we are in the infrared, and so therefore we can use cavities that are 10 microns thick, and we can do microfluidics. We can have liquids inside between 2 plates and just follow the chemistry between 2 plates in the dark. Okay, very important, in the dark. There's no vacuum and there's no light. Okay? And so for that, we developed a system. I'll show you in a second a photo of what we did. So we did chemistry. So we have the mirrors that are infrared transparent. We put some gold or silver. But we quickly realized that chemical reactions ate the mirrors. So we had to put glass. So we put glass, 200 nanometers of glass, to protect the mirrors from the chemistry. So the first reaction we did is very simple. So here you have this cut of a potential energy surface of a molecule, and this vibrational ladder. You split it with a cavity mode, and we looked at this carbon-silicon deprotection reaction, where this fluorine here tacks this carbon-silicon bond and breaks it. Don't ask. I'm not a synthetic chemist at all, so don't ask me any questions about this. We do this through collaborations. And this is a very, very simple reaction that fit it was a proof of principle reaction. When we did this, here are the cavity modes in red. Here's the absorption of the vibrational modes of the molecule. And this peak here is the carbon-silicon vibrational stretching mode. It's going like this all the time, okay? And it has 0-point energy, so it's vibrating all the time, okay? So when you do this, when you tune the cavity and you hit this, you split this vibrational mode into 2, you go from having a rate here outside the cavity or off resonance to a much slower rate, a slow down a factor of 5. Of course, my postdocs and students were very disappointed because they want fast reactions. We live in a fast world, and everything has to be faster. But then they looked at the thermodynamics, and I'm sorry for you, those of you who had not done, I thought of going into thermodynamics. We had some introduction to thermodynamics today. This is classical thermodynamics, macroscopic, but from the thermodynamics of the reaction, you can actually, doing a temperature study of the reaction, you can determine the enthalpy and entropy of the reaction. I'm not going to go into the details, but what's very surprising here is that they change dramatically. The enthalpy doubles, the entropy changes sign, and this is huge. The splitting we have is less than room temperature in energy, and we have 10 times more bigger changes in the thermodynamic parameters. It's very surprising. And to my collaborators, this is a proof of a change in reaction mechanism. The carbon-silicon bond starts breaking before the fluorine attacks the bond. So this was a big surprise to us, and then we decided to go look at other things. So the next thing we decided to target is if we can tilt the landscape just by coupling vibrations. So our collaborator, who's a synthetic chemist, Joseph Moran, prepared a molecule with 2 leaving groups, and so 2 transition states, and with roughly equal proportion of giving yield of one product and the other. And then we want to see if we can tilt the landscape and change the yield, because that's absolutely central for pharmaceutical industry and for all chemical industry. There are some drugs that are not on the market because they're too expensive, they're too impure when they're made. If you're not chemists in the audience, this is important to understand. It's absolutely critical to steer a reaction to the yield, to the product you want, to bring the cost down and the purity up. And so this was a proof of principle, and when we did this, to our great surprise, yes, we can invert the yields. We could start with 60% of one and end up with 20% of one and go 40 of two and to 80% of two. That was a huge surprise to us. But what's even more exciting to most people is this, what we call an action spectra. So what we do is, this is contrary to Emmanuel Bloch's table full of very complicated optics. This looks like this. This is our optical table. Here's our cavity, and with a screwdriver, we tune the whole thing, and it's a sort of a 10-euro experiment, and we tune it across by squashing we have a little spacer made of a polymer, so it's squishable, and we just tune the cavity by squishing this spacer. So when you do this, you can tune across all the vibrational bands of the molecule, and you find that only 3 are involved, okay? And so this is a mechanistic tool without injecting any light. I repeat, there's no light, because people still come to my lab and think we're injecting light into the experiment, okay? There's no light involved in these experiments, except when we take the spectrum, and you can see that only these 3 vibrations, and I'm not going to go into details, but they make sense. But I can tell you now that there are systems we are studying now, which will be for next time or in the future, where you don't expect any vibrations to play any role, and you see a huge effect of vibrations. And in chemistry, there's something called Born-Oppenheimer approximation, where you separate the vibrational part from the electronic part. Well, clearly, you cannot do this as much as we thought. And that's fascinating. So, and we have, okay, if anybody wants to do, if anybody wants to do this experiment, we have a video online, so it's more accessible to people. It's very easy to do. So then we wanted, of course, to do catalysis. And one of the problems with this approach this strong coupling approach to modifying chemistry is that you need high concentration. Why? Because you need to have high absorption to exchange photons, virtual photons, very fast with a cavity in the dark. And one of the dreams have been that we cannot always work with high concentration of reactants. So can we couple, for example, the solvent, which is always high concentration, and transfer that strong coupling to the solute? From a quantum mechanical point of view, this is not possible, strictly, because then even if they have the same frequency, they vibrate at the same frequency, they are not identical, so you cannot do this permutation and look at all the equivalent permutations. It turns out it is, however, possible. You never give up. This is what Stefan Hell was saying before. You should, even if you think something is impossible, it's good to be a bit ignorant, because then you try things which textbooks say it's not possible. So what we did here was we looked at this reaction here, and we coupled this solvent has the same motif, this CO carbonyl stretch here, this carbonyl, COH, and this ethyl acetate, and so they have the same, they vibrate at the same frequency, and we want to see if we could affect this reaction. And then not only could we affect it, but we could catalyze the reaction. Okay, we can accelerate the reaction by an order of magnitude without a catalyst. Okay, you have to understand that we wouldn't be here if there were no catalysis. Okay, there wouldn't be enough food for us. Okay, on this earth. We'd be a smaller population, have less problems, but there would be far fewer of us here. So, catalyst is the basis for all the material science, all the way from pharmaceuticals to chemicals to materials, okay, to fertilizer. And so, catalysis is very important. And here you see this huge acceleration. You see the auto-tune cavity gives nothing but on cavity. And here we have done some carbon-13 experiment to show that it's really a transfer, and now there's theory to go with it. You can show that you can transfer because all these, it's just like the metronome, all these vibrations are now vibrating in phase. And a solute inside that also has the same vibration starts, of course, it's driven by this thing. Okay, we see this also not only for chemistry, but we see it also for things like superconductors. We can modify the TC of superconductors by the same principle, by putting superconductors in a polymer and driving them. Okay, so this is a very powerful way, but it shows that you can do catalysis. Now, some people think we're the only ones who can do this. No, there's a group in Japan who has 4 orders of magnitude catalytic effect in a cavity. Okay, so this is just an order. So 10,000 times. And you can also modify enzymes. So once we understood this, well, that's great. We can just couple water. Water is the basis of life. We can affect enzymes are full of water. And we chose pepsin. Pepsin is what's digesting your lunch right now in your stomach. Okay? They're eating up, breaking up the protein and cutting it in little pieces so that you can extract the good things from it. It involves water in the active site. It involves water in the tertiary structure, the complete structure. And there's water outside. And we thought, well, this has to perturb it, and indeed it does. Oops. So it vibrates. They're actually water because there are only 3 atoms, have very few modes, vibrational modes. So there are 2 stretching modes, symmetric, antisymmetric, and a bending mode. It turns out that only the stretching modes perturb the chemistry, not the bending mode. That tells you something about mechanistics. Here you see it reduces the activity, but it's still amazing that you can see this on the thing. It's a very difficult experiment. The last thing I'm going to show you is energy transfer. So energy transfer occurs in plants. Okay, actually probably there would be no plants in this part of the world if there wasn't for energy transfer. So the flux of light from the sun is so weak that at the scale, molecular scale, there are not enough photons coming in to drive the chemistry that follows. Physics terms, it's an impedance mismatch. So you have the thing coming in, and there's a rate of photons being absorbed, and the chemistry that follows has to be pushed at a certain rate to be efficient. So plants adapted away from in weak areas where there was little sun by creating antennas and chlorophyll antennas that catch the light and transfer it to a reactive center, thereby increasing the rate by all it took was 300 times. So there's typically 300 molecules, antenna molecules for one reactive center to drive the photosynthesis. And this is known as energy transfer, and it goes as first they did the theory, and it goes as 1 to the power over R6, so distance between the molecules. So as soon as the molecules are more than about 10 nanometers apart, this doesn't occur anymore. So we want to see if we can enhance this, because now we have these collective states. So how do we do this? Well, what's very interesting with these light matter strong coupling is that I can couple one molecule, the donor, that one we're going to pump to transfer the energy to the acceptor. We can couple this and make 2 hybrid light matter states. But because they have 50% photonic content, we can use them again to mix with something else. So we use them to couple to accept the molecule, and now we have a 3 hybrid light matter states, and these donor and acceptor are actually quantum mechanically entangled. Okay, so now they are actually like in a they're all talking to each other. Okay, and on top of it, we have this collective effect. It turns out also that this lowest light matter state, called polaritonic state, is mostly acceptor, and the upper state is mostly donor. So you can inject photons in here and see if they come out here. Okay, and that's how you do it. So to make a long story short, this works very well. You can enhance the energy transfer to the limit, practically 1, the rate goes up, and the actual energy transfer. But so that's nice when they're all mixed, but then you can do an experiment which had never been done before, is you can separate the donor and acceptor in space and see if the entanglement plays a role. And you can transfer energy over distances you never could do before. And this is what we did. We put the donors on one side of the cavity, the acceptors on the other, and put a spacer in between. And actually, it works very well. You can transfer, I'm not going to show all the time, I don't have time, but you can transfer energy from in this system over distances that are unheard of before. Actually, the theory tells you that there's no more distance dependence. So you're no longer in the Förster regime. Okay? So, I hope I've convinced you that there's light in the dark with QED. Okay, there's something you can do. You can play with this. It's a new tool for chemistry. You can affect reactivity. I didn't talk about dynamics, thermodynamics. It affects the thermodynamics, needless to say, and dynamics. You can also affect material properties. I mentioned briefly, because you have these delocalized states, you can enhance conductivity, energy transfer I just showed you. You can also change superconductivity phase transitions. So we just have we have a paper online which shows that you can change the TC by 50% for C60 rubidium-3, which I worked on when I was young, and you can actually go from 30 to 45 degrees by Kelvin by doing this. If we could do this with high TC material, it would be even more interesting. We've tried, but there is the reverse. When we do this with high TC material, we'd actually lower the TC. Okay? Like YBCO, we lower the TC, but it shows that phonons play a role. So I didn't do this by myself. This is my team of people, and this obviously they did all the work, and this is what every day I wake up, I look forward to meeting them and hearing about the results. So thank you for your attention.